Hi guys, I'm Andrew Abdallah and I'll be doing a video tutorial for chapter 15, your chemistry book, which is chemical equilibrium. And you shouldn't use this video to study for the test because the examples used in this video tutorial are going to be not, they're going to be much easier than the ones on the test. So don't expect that this will prepare you for the test. It gives a good summary of the chapter, but once again, do not use this to study for the test, okay? Uh, so, I guess we can start off with what is chemical equilibrium? Well, chemical equilibrium occurs when opposing reactions are proceeding at equal rates. So if a reaction is at equilibrium, the reaction is written with a double arrow. So it would be like this, A going to B with a double arrow. Okay? Because the rate of the forward reaction is equal to the rate of the reverse reaction. Okay? So, now there's a law of massive action which says the relationship between the reactants, and it just gives the relationship between the reactants and products at equilibrium. Basically saying, okay, so you have A and then A, so this is going to be the coefficient, and this is going to be the chemical species, plus the equilibrium with lowercase c, and then c, and then lowercase d, and d. And so it just says, it takes this, and it's saying, okay, this right here, this reaction can be expressed as Kc equals concentration of C raised to its coefficient, concentration of D, the chemical species, raised to its coefficient, over concentration of A raised to its coefficient, over concentration of B raised to its coefficient. And you look and you say, okay, well, these are products, these are reactants, so it's concentration of the products over the concentration of the reactants. Okay? Now, we have the Kc is going to be called the equilibrium constant, and this is called the equilibrium constant expression, okay? And so, in chapter 14, you learned, which was the chemical kinetics chapter, you called these exponents right here, called these orders, okay? But in the equilibrium expression, these exponents are the coefficients of the chemical species, not the orders. So just don't worry about orders in this chapter. But there is an exception, like there always is in chemistry. Solids and liquids are not included in the equilibrium expression. So solids and liquids aren't. However, aqueous solutions and gases are included in the equilibrium expression. So solids and liquids are not included in the equilibrium expression. Okay? So, now, you might ask yourself, well, why? I mean, they're reactants or they can be products, so why shouldn't they? Well, solids and liquids aren't, because their volume is negligible and their concentration constant, so that they have no effect on the equilibrium of the reaction. So, let's do an example of the Haber process for synthesizing ammonia. Let's do N2 gas plus 3H2 gas goes to 2NH3. Don't forget the double arrow because it's an equilibrium. So how would you write this? Well, they're all gases, so products or reactants raised to their coefficient. So NH3 squared over H2 cubed N2. right? So that's how you do it. But let's take a different scenario of 4HCl gas plus O2 gas. It's in equilibrium with 2H2O gas, liquid plus 2Cl2 gas. Okay? So in this one, what do you see? You see gas, gas, liquid, gas. So you see liquid, so it's not going to be included in the equilibrium expression, and it's just going to be Kc equals Cl2 squared over O2 squared HCl to the fourth power. Or O2 is not squared, sorry. HCl to the fourth power. Okay, so that's pretty basic, simple to start off. But let's move into some other applications of this. So you can replace partial pressures with molar concentrations to get the expression Kp equals the partial pressure, and we're still looking at this right here. So C and D are products, A and B are reactants. So partial pressure of C, which is the chemical species, raised to its coefficient. Partial pressure of D raised to its coefficient over partial pressure of A raised to its coefficient, and partial pressure of B raised to its coefficient. Okay, so these chemical species, these are the coefficients. Okay, now, I mean, you can relate partial pressures and molar concentrations in the expression Kp equals Kc times RT delta N. Okay? So this is, you know what Kc is. It's the same thing as Kp, but instead of using partial pressures, it uses molar concentrations. Okay? So you have the Kc, and you know the Kp. Now what is R? Hopefully you know what R is by now, because chapter 10, ideal gas law. Exactly. So R. Now don't think that whenever you see R, it's automatically 0.0821. Okay? Because as you'll find out later on, R can change values. Alright? It's all based on the units. If you write out the units, you'll be able to know what R to use. Okay? T, hopefully you know what T is based on the ideal gas law. T is in kelvins, so it's however many kelvins. Now delta N, take delta H. You've probably seen that before. Delta H is like, it's the delta H of formation of the products minus the delta H of formation minus the reactants, and of course times the number of moles on both of those. But it's products minus reactants. So what would you think delta N is? Yeah, number of moles of products minus number of moles of reactants. So that's what you would have, right? So this is the change in moles. Hopefully, again, you know that from the ideal gas law. That you know that N is moles. Okay, so let's do an example. Here's an example. So let's say Kp equals 34.5 at 305 Kelvin. Okay? And you're given the expression SO2 gas plus Cl2 gas goes to SO2 Cl2. Yes. Okay. So what do we do? And we're trying to find Kc. So we're given Kp and the temperature, which is T. And we already know R, right, because it's a constant. So let's write out our equation. Kp equals Kc RT delta N. Okay, so you have Kp, which is 34.5, equals Kc, which is the unknown, times R, which is 0.0821, times temperature, which is 305. And all of that is raised to delta N. Well, let's see, delta N, products minus reactions. So we have 1 mole here, 1 mole here, and 1 mole here. So 1 and 2, 1 minus 2 is -1, so raised to -1, okay? And so that turns out to be Kc is going to equal 864. Okay? So let's move on. There's something called, this is just for definition, there's something called heterogeneous equilibria, and homogeneous equilibria. So you can kind of tell the difference. Heterogeneous is where all the chemical species in the reaction, they don't have the same states, and by states I mean like gas, solid, liquid, aqueous, same states. But let's take homogeneous, okay, equilibria. That's where they all do have the same states. The chemical species they all do have the same states. Okay, so let's take the Haber process. Okay, right, we had that before. Right, N2, so H2 goes to 2NH3. Well, what do you think this would be? Exactly, homogeneous reaction, so equilibrium. So, you know, this is just vocabulary in case there's that one question on the test or exam or AP test, hopefully. So you know this. And then, so this is just pretty simple. We can move on to the little harder stuff. Okay, a mixture of 1.374 grams of H2 and 70.31 grams of Br is heated in a 2-liter vessel at 700 degrees Kelvin. These substances react as follows. So, the reaction that we have is it shows H2 gas plus Br2 gas goes to 2HBr gas. Okay. So you notice I wrote an R right here. I wrote an R because I'm making a rice box. So rice boxes, whenever they ask you to find, like in this question, they're asking us to calculate the equilibrium. At equilibrium, the vessel is found to contain 0.566 grams of H2. Calculate the equilibrium concentrations of H2, Br2, and HBr. Calculate Kc. So whenever they ask you to calculate equilibrium concentrations, or calculate Kc, or calculate the pH, which you'll find later in chapter 16, you probably want to use a rice box because it really helps you organize. So R is for reaction, I for initial concentrations, C is for change in concentrations, and E is equilibrium concentrations. Okay, so you're trying to find E. But you're given 0.566 grams of H2, so you already have an E. But let's start off with the initial. So you convert the grams of H2 to moles, and then divide it by 2 because that's the liters to find the molarity, and you end up getting 0.3435 molar, 0.219 molar, and then this is 0 because at the initial you're not forming, you don't have any of that at the very initial, so you assume it's 0. And then you're given the equilibrium for H2, and you convert to moles, divide by 2 to find molarity, and you get 0.142 molar. So, but you don't have these. So what you do is, okay, you have initial and equilibrium, which is kind of like the final. Think of it like the final, but it's not really. But think of it. This is change. So change must be difference between these, right? So how do you get from 0.3 to 0.1? You obviously subtract. You end up subtracting 0.202 molar. Now you can use stoichiometry because look, you have 1 mole of H2, 1 mole of Br, 2 moles of HBr. So, and they're all gases, don't worry. So you have the stoichiometry, so if this is 1 to 1, then this is going to be 1 to 1, so this is also going to be minus 0.202. When you have reactants, you're subtracting. When you have products, you're adding because you're losing these, gaining these. Okay, now look, H2, 1 to 2, so this is going to be 1 to 2, so 0.202 is going to become plus 0.404 molar. Alright? And so you're going to find these by simple mathematics. Molar, and it's going to be 0.404 molar. Okay, now you have the equilibrium concentrations. What can you do? Put them in the equilibrium constant expression. Kc is products over reactants, okay? Products over reactants. So you get products. Careful, this is a coefficient, so you must square the product concentration. So you get 0.404 squared because of the coefficient over reactants are just 1, so you don't have to square anything. 0.017 molar and 0.142 molar. And Kc equals 67.6. Okay, so let's move on to another topic. There's something called Q. Q is the reaction quotient. Okay, and it's still going to be products over reactants, don't worry. But it's different than Kc. See, Q can be at any given time, not necessarily at equilibrium. Okay, so at any given moment they give you on the AP test, it's Q, not necessarily at equilibrium. So they can say, so let's take examples of what they can say. What if Q is equal to K? Q is equal to K, okay? Right? What would you think? Well, K is at equilibrium, so if Q is equal to K, K must be at equilibrium. So reaction is at equilibrium. Now if Q is greater than K, think about it like this. What is K? K is also products over reactants, and so is Q. So if Q, what can you make in this for Q to be bigger? You increase the products because their concentration of products are proportional to Q. So increase the products, decrease the reactants, will increase Q. So if Q is greater than K, there will be more products and less reactants. And to compensate for that, you have to shift left to establish equilibrium. Okay? So if Q is greater than K, that means there are more products. Shift left so you can gain more reactants to compensate for those increase in products. So shift left to establish equilibrium. Right? Now what if Q is smaller than K? You can probably say, oh, it's the opposite. So shift right. Well, again, you think about it conceptually. So Q is products over reactants. So that means reactants are increased, products are decreased because Q is smaller than K. So that means there are more reactants, which are on the left side, than products, which are on the right side. So that means you have to shift to the right side to gain more products, to compensate. So shift right to establish equilibrium, okay? Alright. Now that we have that down, we can do an example, alright? So, let's say, okay, so we're given the reaction at 450 degrees Celsius. The equilibrium constant is 51, okay? So you're given case, here's an example, Kc equals 51, and the reaction is H2 gas plus I2 gas, equilibrium with 2HI gas, okay? So let's say H2 and I2 both have the same concentration of 2.0 times 10 to the negative fourth molar, and let's say 2HI has a concentration of 6.5 times 10 to the negative second molar, okay? So what you do, so it's not, so you're given this situation, so this is going to be Q, okay, not K, because, I mean, these aren't at equilibrium necessarily. So Q, which is equal to products over the reactants, equals concentration of HI. Again, this is squared because, don't forget, this is the coefficient on HI. It's going to make it squared because it's raised to the coefficient. But these have a coefficient of 1, so you don't need to square the reactants. H2, I2, that's going to equal 6.5 times 10 to the negative second squared over 2.0 times 10 to the negative fourth squared. And I did that because these are the same, so you're multiplying 2.0 times 10 to the negative fourth times 2.0 times 10 to the negative fourth, so you're just squaring it essentially. Don't think that this is not a coefficient, just don't think of it that way. It's just I'm multiplying the same thing twice, so it's squared. And this turns out to be a pretty big number. 105,625 is the Q, and hopefully you know this is much bigger than 51. Okay, so you know that since it's way bigger than 51, equilibrium will lie to the left. Well, yeah, so by that I mean you have to shift left. So to establish equilibrium, you must shift left. Okay? So you can increase the reactance. Because right now there are a lot of products, because this is so high. The products are proportional to Q, so products must be high. So to shift left to increase reactance to compensate. Okay? Alright. Now, the last thing in the chapter. I know when you probably saw this happened with me too. You're like, what is Le Chatelier doing? Like, this is just so confusing. But it's really not. It's really actually fun when you're able to get it, because when you get these kind of questions, you feel happy because they're so easy once you understand them. Okay? Now I'm not gonna say that they're all easy, but you'll want these questions, right? So Le Chatelier, his principle, I'm just gonna call it Le Chat. Le Chat's principle says that if a system at equilibrium experiences a change in temperature, pressure, or concentration of one of the reactants or products, the system will shift its equilibrium position to counteract that change. Alright? So there are three things which can cause a change. You got one, adding or removing reactant or products. Okay. Then you have two, changing, which, and by that I mean increasing or decreasing the volume of the system. And then you got three, changing the temperature of the reaction. Okay? So you have, I'm just going to use one example and one example only for this, all of these, and I'll use it for the same, I'll use it the same thing. So that example is, we have the reaction PCl5 gas goes to an equilibrium with PCl3 gas plus Cl2 gas. Okay? And with a delta H equaling positive 87.9 kilojoules. Now, when you add or remove reactant, okay, or product, you must shift to the other side of the reaction to compensate for that change. So let's say you add more PHCl5. What you need to do, so that you added more reactants, you add more products. You add these concentrations increase. If you increase this, you must increase this to stay the same. Alright? Now let's say you add products. So you added more of these, you must add more reactants. So you make these you make Cl2 concentration higher, PCl5 must be higher. Okay? And then you remove reactants, okay? You have, let's say you remove PCl5. Well, to compensate, you must add more PCl5 and go this way. So you'll lose these to gain and make this gain more reactant because you lost it. So you'll shift this way, lose product to compensate for that loss. Okay, same thing, when you remove reactant, you must shift this way, right, this way, and you'll lose PCl5 to compensate for that loss in products. And it can only be one of the products. It doesn't have to be both. Okay? So let's say I remove PCl3. What do you have to do? Shift this way. Sorry. Shift this way. So you lose PCl5. And there'd be... So, yeah. You shift this way. So that's what he's saying. Just you counteract that change. Let's say you change volume. Well, what happens if you change volume of the system? You also change the pressure. And I'll tell you right now, pressure and volume are inversely proportional. So, increasing volume decreases pressure. And when you do this, when you increase volume, then you decrease pressure, you also increase, you shift to the side with higher moles, higher number of moles. So shift to higher number of moles. Okay? So you have a higher volume, you shift to the side with a higher number of moles. And it's the opposite. Lower volume, higher pressure, shift to the side with a lower number of moles. Basically, they won't really talk about pressure that much. But if they do say, like, they increase pressure, then you know this. But usually they'll say volume, but you should still know. So when you decrease volume, increase pressure, shift the side of the lower moles. Okay, so let's do an example. Let's say I decreased volume of the system. So where would I shift? So that means I decrease volume, increase pressure, shift to the side with lower number of moles. This has 1 mole, 2 moles, this has 1 mole. So shift lower side. You're losing products, gaining more reactants, okay? Because you're shifting to this side and you're losing those products to make more reactants. Alright? Now, the final one is changing temperature. When the reaction is endothermic, and you increase the temperature, the K will increase. And then if you decrease the temperature, K will decrease. But when it's exothermic and you increase the temperature, K will decrease. But then when you decrease the temperature, K will increase. Sorry, this isn't very, it's really hard to see that writing, but, so, this is just basic. I mean, you're gonna have to memorize this, unfortunately, but, I mean, it's not that bad, because the way I think of it is like, okay, endothermic, what are you doing? You gained heat. So then if you increase the temperature, you gain heat, this will go up. So K will go up. Now it's exo. Exo, you lose heat. Now when you lose more heat, like temperature goes down, K will go up. So when the temperature follows what the reaction is, the K will increase. And then the rest you can just remember that they decrease. So let's say let's say it's exothermic and T decreases. Well, you know, exothermic means you lost heat, and then on top of that, T decreases, so K would have to increase, because you're decreasing temperature just like it's exothermic. This is just the way I think of it. You can just think of it whatever way you want, but you just gotta know this, all right? So let's give an example. So I had the delta H here. Delta H, 87.9 kilojoules. Okay, so you know it's endothermic. So let's say I decrease the temperature. Try not to look here. If I decrease the temperature, okay, then which side am I going to shift? You decrease temperature when it's endo, you also decrease the K. Okay, so when you decrease the K, what are you also decreasing? If K is products over reactants, you decrease K, you decrease products, you increase reactants. So decrease products, increase reactants. So that means, excuse me, sorry. So K is going to decrease, so you're forming more reactants. Alright, so you're going to form more reactants because K is decreasing, and reactants are inversely proportional to K. So you shift this way, alright? And I guess there's one more category to cover, and it's just catalysts. So catalysts increase the rate at which equilibrium is reached. Just a definition. You know, just catalysts lower the activation energy, so they increase the rate of the reaction. That's what you learned in chapter 14. So here, catalysts, they would increase the rate at which equilibrium would be established. So you reach equilibrium faster. And however, catalysts don't change the composition of the equilibrium mixture. Okay, so they don't change the composition. They just increase the rate at which equilibrium is reached. So that's all I have for you guys. I hope you learned a lot. Alright, thanks guys.